All right, let's look at another conservation of angular momentum problem. This one with two spinning disks. So we're going to have two spinning disks. They're going to be spinning on top of each other. They have a similar size and shape so that they have, one of them has moment of inertia I, spinning at angular velocity omega, and the second one is rotating in the same direction. So they both have, let's say, a positive omega. And they're identical. There we go. So this one also has a moment of inertia I. So the one rotating on top, so let's draw a picture of our disks. All right, this one is going to have some omega, let's say counterclockwise, which is 2 omega, and it has moment of inertia I. And then I have our second disk, which is the same size and shape, and it's rotating about the same axis, but at a rate of omega, same I. So this becomes a system-type conservation of angular momentum problem. So what's going to happen, I'm going to drop and lower the top disk onto the second disk. And the force of friction is going to engage, right? One's spinning at a higher rate, so they're going to be exerting the force of friction against one another. But as they exert the force of friction, the torques due to friction are internal within the system. So remember, we said in the initial notes, in order for the angular momentum of a system to change, you must have an external torque. So whatever the total momentum of, let me get a different color here, the two-disk system was to begin with, so like we've done with system problems, I'm going to define my system as the two disks. Whatever their initial angular momentum was must be the same after the two disks come together, because the force of friction acting between them will be exerting equal and opposite torques on both disks. All right, so afterwards, let's draw a picture. So now I'm going to have two disks, and they're smushed on top of each other in one big pile. And we want to figure out what's their new omega final after they interact. Okay, so this is a conservation of angular momentum problem. So delta L is going to equal 0. So the L initial is going to equal the L final. I'm going to slide this over here. Now L initial will be the L of disk 1, which will be I times 2 omega, plus the I of disk 2, which is I times omega. Since they're rotating in the same direction, both positive from a counterclockwise rotation. Now that has to equal now the angular momentum final. Well, now they become a combined disk, so I have I of the first one times omega final plus I of the second one times omega final, which just becomes 2 times I times omega final. So if I add together on the left-hand side, I have 2 omega I plus omega I, which becomes 3 I omega, or omega I, however you want to do it. And that is going to equal to 2 times I times omega final. I cancels on both sides. And then I'm going to divide by 2. And what I get is the final angular velocity is going to be 3/2 omega. Or, if you look at it, halfway in between the omega of the bottom disk and the top disk. So this will lose 1/2 omega units of angular velocity. Well, this gains 1/2 omega units of angular velocity, and that's how you can see that conservation of angular momentum works for rotating objects that come together with internal torques.